The positive Grassmannian, so last time we talked about Grassmannians as generalizations of just projective space. And there's all kinds of things that we can do in projective space, and we're going to start learning how to generalize them into this space. So projective space is a space of lines to the origin in n dimensions, and we can generalize to the space of k-planes to the origin in n dimensions. And what we're going to try to learn how to do is to generalize a lot of familiar geometric notions from projective space into the Grassmannian. So the first thing that we're going to generalize is the notion of a simplex. Okay? So, and that's what the positive Grassmannian is. It's a generalization of the notion of the quote inside of a simplex into the Grassmannian. So let's begin by talking about this again, for example, the inside of a triangle. So we know, as we've discussed many times, the inside of a triangle, I can think of all the points on the inside of this triangle as associated with three coordinates, C1, C2, and C3, where all these C's are positive. Okay, if all the C's are positive, then projectively that's sweeping the entire interior of this triangle, right? Okay, and note here that I could say either all positive or all negative. Projectively, it doesn't make any difference. But I'm going to be saying all positive from now on. And that's associated with the fact that we already saw when we talked about these cones, that when we have these interesting interior regions and all these things that we're talking about, it makes sense to talk about projective transformations that are just positive, where the overall rescaling is just positive. Okay? So we have these lines through the origin, we have the other side, but if all the vectors were sort of on the same side of some hyperplane, then it makes sense to sort of talk about the ones on one side, the ones on the other side, and so we can just talk about things up to positive rescaling. Or you don't have to. You can talk about rescaling everything, but then remember that only ratios matter. So when we say positive, we mean either they're all positive or all negative. All right? So I'm not going to keep saying that. I'm just going to slip into the usage all positive. The other thing is that even though we're going to allow that to be equal, greater than or equal to 0, so what does it mean for any of these C's to vanish? So let's say, what does it mean for C1 to vanish? If C1 vanishes, it means that you're on the line 2, 3 in this picture. So having the C's vanish means that you're on the boundaries of the triangle. If I have C1 and C2 vanish, that means I'm stuck at the point 3. Okay? So really, I should be calling this, therefore, the non-negative. All these numbers are non-negative, but I'm going to keep saying positive, okay? Because we're going to be saying it a lot. And so by positive, I always mean non-negative. OK? So that's a notion of the inside of a triangle. The notion of the inside of a simplex, in general, is just a C1 through Cn, where all the C's are positive. Okay? No. Remember, we're thinking about things. We're now thinking this is a 3-vector. 3-vector. We're thinking about this projectively. Okay. So if you like, we're really thinking about the space of lines through the origin, right? So then I have this line 1, 2, and 3, and I'm just sort of thinking about everything that's inside this cone. If I think projectively, the whole beauty of it was what we saw already before, is that I get, it divides the divide by C1 plus C2 plus C3 for you automatically. Okay? Okay, so then let's pause. So what have we done? In the space of lines through the origin, in the space of all lines through the origin, there's a positive part of the space that we can identify as the inside of a simplex, where we say that all these C's are positive. Okay? Is that clear? So that's the familiar notion of a simplex. And what are the boundaries of a simplex? So I don't know, we can call this an n-1 simplex. The boundaries of Sn-1, simp n-1, are just where I set any of these c's to 0. Like I can set any cb to 0. And then what does the boundary look like? It's just a lower simplex, right? So the boundaries are also simplices. OK, so this is a very simple and familiar idea. And now we're going to generalize it. So now let's say you give me the space of k-planes in n dimensions. Okay, so we saw last time that a k-plane in n dimension is just specified by giving some k by n matrix. And again, in the case of a simplex, it was not just abstractly the projective space. I had n preferred directions, right? I had some c1. I had the directions 1 through n. So similarly here, there's columns here, 1 through n. So I'm imagining that there are n preferred directions in this space that I'm using to label my columns. So I have this k by n matrix C alpha A. And now what I want to know is what could the analog of the simplex be? So the analog of the simplex is to put some kind of positivity conditions on this matrix. OK? But what could those conditions be? So what's the absolute dumbest one? They could be all the entries are positive, right? That's the dumbest one. You should always do the dumbest thing in life first. Rule of physics. Dumbest thing works almost 90% of the time. This is one of the rare instances where the dumbest thing doesn't work. OK, so what's wrong with this dumbest thing? What's wrong with saying all the entries are positive? It's not invariant under these GLK transformations, because it has to be a statement about the k-plane, right? So for it to be a statement about the k-plane, it has to be a statement that's invariant under doing any k by k linear transformations on this guy. So I can't just say the entries are positive, because that's obviously not invariant under k by k linear transformations. And what are the objects that we have at our disposal that are invariant under k by k linear transformations? They're the minors, right? The minors that are invariant, well, again, the ratios are invariant. There's the overall GL1. But what we can say is that all the minors are positive. So that's the next thing, second dumbest thing. All the minors are positive. OK? And this is almost right, but we have a little problem. What is our problem? Why can't I just say I have 2 by... Why don't I say I just have a 2 by n matrix? Why don't I just say all the minors AB, all positive? This is an obvious problem. Huh? Right. The problem is that the minor 3, 1 is negative 1, 3. So I definitely can't say that they're all positive, right? OK, so now that's something we did not encounter for the simplex. See, for the simplex, the condition that all the c's are positive is completely permutation invariant. I don't have to order the c's in any way. But here, if I want to generalize this notion to the Grassmannian, I just can't do that. There is no obvious permutation invariant notion of positivity. Okay? So what we need to do is give an ordering. Okay? So you just give some ordering, which we've sort of tacitly done, 1 through n. Okay? And now we'll ask, therefore, that all the minors are positive in that ordering. Okay? So we're going to say that all the minors A1 through AK are positive when A1 is less than A2 is less than AK, when everything is ordered. Okay? That's it. That's the positive Grassmannian. Okay? It's that part of the space of k-planes in n dimensions where this condition is satisfied. Yes?
This is just, invariantly, this is just an orientation of the n-dimensional space that you're looking at k-planes in, right?
Sorry?
This is just an orientation of the n-dimensional space.
What is an orientation of the n-dimensional space?
This ordering.
It is not invariant under GLN. Absolutely not invariant under GLN. It is, so it is not invariant under GLN. And that's we don't have a GLN symmetry in our problem. Okay? Yeah. Nope. There's no trace of full GLN invariance. Okay? We don't even have full GLN invariance for the, we don't have full GLN invariance even for a simplex. Okay? We definitely don't have full GLN invariance. For the simplex, we have the subgroup of GLN, which is permutations. Okay? We can permute the columns any way we like. Okay? And that leaves the simplex invariant. And for the positive Grassmannian, we have less. We have to give an ordering for the columns. Okay? Actually, the first thing that I want to do, though, is ask how much we have left. But your question is a good one. How much do we have left? And what we almost have left is a cyclic symmetry. Okay, so there is a cyclic, or what's called the twisted cyclic invariance. You see the word for the, and that's simply the following. So let's illustrate with G plus 2n, which we're going to talk about in a second. But so let's say I have all the ABs are positive, which means in particular that I have like 1, 2, 1, 3, blah, blah, and 1n is positive. Okay, so I'm saying they're all positive in some ordering. Okay, so it's 1n, not n1. Okay, so this is the definition. Okay, you just say all the things in this ordering are a positive. Okay, but now if you take the column CA and just shift it to CA plus 1, then they're almost all positive again, right? For example, 3, 4 will go to 4, 5. 3, 7 will go to 4, 8, right? So they're all positive. The only problem is the ones that are going to wrap around the end, okay? So, and for example, in this case, 1n is going to turn into n1 on the other side, right? Sorry, 1n is going to turn into 2, 1 after I shift everything over by 1, right? Okay, so that's not an invariant. So all you have to do to fix that problem is to say that the end, that the Cn goes to minus 1 to the k C1 under this shift. Okay, so anything that wraps around the end picks up a factor of minus 1 to the k minus 1 when you go around the end, right? Okay, because all that's happening when I shift something over, I might have to move something that was at the end to the beginning to put it in order, and it's passing through k minus 1 columns as it goes through. Okay, so you have to add this little annoying minus sign at the end when k is even. Okay? Right. So that's the subgroup of the GLN that we have left that acts nicely. Okay, so if you give me one positive k by n matrix, I can get another positive k by n matrix by cycling all the columns over with this minus sign when things wrap around as needed. Okay? Absolutely. That's just what we're going to talk about right now. Okay. Okay, so let's look at the first interesting example of the positive Grassmannian, which is G24. It's the first interesting example of the Grassmannian, so we can look at actually, you might want to, let's just quickly see that for, so what is I'm going to use this notation. What is G plus 1, 3? Well, this is just C1, C2, C3. Say G plus 1n. It's a 1 by n matrix, and all the minors are just the CA's positive. So of course, that goes back to the simplex. Let's look at G plus 2, 3. This is very slightly more interesting. Remember, G plus 2, 3 is the same as G2, 3 is the same as G1, 3. So this is not really new, but let's see it explicitly. So this is a 2 by 3 matrix. I can always gauge fix it remember, I can put a 1, 0, 0, 1 anywhere I like, so I can put it there. So let's look at the rest of the, yeah, x, y is fine. So what do I have? I just have the space where x is positive. That's the minor 2, 3. The minor 1, 2 is y is positive. The minor 1, 3 has been gauge fixed to be 1 already. Okay? So again, that's exactly just a simplex, right? All right, so the first interesting example is G24. And let's go through this example in a little bit of detail. So let's just get an idea. This is some configuration of 4-dimensional vectors, of 4 2-dimensional vectors. So let's just geometrically remind ourselves, what does it mean for the minor AB to be positive? So let's say I put A to be 1, 0, and B to be x, y. Okay, then the minor AB is just y. Okay, so that means that if A is pointing in this direction, where can B be? So so if this is A, if this is the 2-dimensional vector A, then B has got to be somewhere up here, right? If A was 1, 0, if this is the x-axis, B has to have a positive y coordinate. So B has got to be here somewhere. B has got to be there, say. Okay, or there. But it can't be here. Okay, so let's just see what some configuration looks like. So let me actually draw you what the typical configuration looks like. Okay, so that's what it looks like for a typical configuration in G plus 2, 4. Okay, and let's see again why it's true. Well, 2 is on the right side of 2 is on the right side of 1, 3 is on the right side of 2, 4 is on the right side of 3, but also 4 is on the right side of 2 and 3 is on the right side of 1. Okay? You'll notice that okay, so now how can I go to the boundaries of this space? The boundaries of this space are when the minors go to 0. The minors go to 0 means when some of these vectors become parallel to each other. Okay? So how do I go to the boundaries of the space? Well, what can I do here to approach a boundary? Like, for example, I can make 2 and 1 parallel to each other. So let's just draw a bunch of pictures. Okay, so for instance, I can make 2, 1, and 2 both parallel to each other, and I still have 3 and 4. Or any of the other ones, right? By the way, I can also make 1 and 4 parallel to each other, right? I can make, that's also a boundary. 1, 4, 2, 3. Okay? So notice something slightly cool here, that the boundaries are when 1, 2, the first boundaries, if you like the codimension 1 boundaries of this space, are when 1, 2, 2, 3, 3, 4, or 1, 4 go to 0. There are 4 of them. Okay? Now remember, all we demanded was that all the minors were positive. So at 0th order, it looked like all the minors were on an equal footing. Okay? There was an ordering, but we said all the minors have to be positive. But somehow having all the minors be positive has put in a little bit more of a relationship between them. The consecutive ones are special. Okay? For instance, I couldn't put the minor 1, 3 to 0 to go to the first boundary, right? Why can't I put 1, 3 to 0? Well, from the picture, it's clear. I'm trying to put 1, 3 to 0. I'm trying to, put 3 on top of 1, but I can't put 3 on top of 1 because 2 is squeezed between them. Okay, so I have to either put 1 on top of 2 or 2 on top of 3 in order to be able to eventually put 1 on top of 3. Okay? Now that we see very easily from the picture, but we can also see it very easily algebraically. And this is the key difference between the simplex and the Grassmannian. In the simplex, we didn't encounter this phenomenon. We had a bunch of boundaries. I could go to the boundary. I have a bunch of inequalities. I can go to the boundary just by saturating any one of them, setting any one to 0. Then I go to a lower simplex. But it's not true in the Grassmannian. I had a bunch of boundaries. I had a bunch of inequalities. But I can't send any one of them to 0 willy-nilly that I like. And we see this algebraically by the fact that these minors are not independent, and they satisfy these Plücker relation, this one Plücker relation in this case, right? And now you can see why we've started writing this Plücker relation that is, as physicists, we always write in a cyclically invariant way, something plus something plus something equals 0. It's a little funny to write it as something equals something plus something, but it's because we now care about positivity, okay? So if you look at this equation, you see what the problem is. Everything is supposed to be positive here. All these minors are supposed to be positive. So this equation is consistent, positive equals positive plus positive. But I can't set the left-hand side to 0. I can't just set 1, 3 to 0 without setting other things here to 0 as well. Okay, so these nonlinear Plücker relations, just these dumb quadratic relations, are what gives an enormous amount of extra structure to this space. We're not just saying that we have, yeah. If you like, a uselessly fancy way of saying this is that it is just a simplex, but in this higher dimensional space of where the Grassmannian lives in the Plücker embedding. In that giant space of all these n choose k minors, there is this quadratic surface that restricts you down to the positive Grassmannian. And we're talking about the intersection of that quadratic surface just with a simplex that says all the minors are a positive. Okay? So there's something fundamentally curvy about it. Okay? So it's the intersection of this giant simplex with this quadratic surface. Or you can just say that these positive variables satisfy a bunch of nonlinear relations. But already we saw something sort of amusing here, which is that consecutivity made an appearance, right? I plus 1 mattered. 1, 2, 2, 3, 3, 4, 1, 4 mattered. OK. Now, this is what I'm about to do now is not at all deep. It's just a useful way of allowing you to visualize slightly more. And we're not going to be visualizing terribly much more. But it's useful to see some 2- and 3-dimensional examples. So here, G24 already is a picture is a 2-dimensional picture, right? This is not a projective picture. These are honest 2-dimensional vectors, right? They're honest 2-dimensional vectors. But it is useful to just imagine extending all these rays out and just seeing what the picture would look like if you intersected it with a line. Okay? The reason this is possible is that if you rescale all of the columns by a positive number, you're not going to change any of the positivity properties. Okay? So that's all we're doing. When we're drawing this picture is we say, I'm free to imagine rescaling all the columns by a positive number. And so if I do that, I'm just talking about the rays going off in this one direction, and I can look at the intersection of this picture here. That just makes it slightly more convenient to think about. We can just go down one in dimension and thinking about it. It's not deep. You don't have to do it. But in this one-dimensional picture, this is what the G24 looks like, right? And now, what do some of these first boundaries look like? Well, we've talked about what they can look like. They can look like 1 on top of 2, and then 3, 4, 1, 2 on top of 3 and 4, 1, 2, 3 on top of 4, and then we have 2, 3, 4 on top of 1. Okay? So these are the codimension 1 boundaries. Let's keep going just to see what else we can do. So let's say I've already gone to this situation where I've made one parallel to 2. What else can I do now? Okay. Now there's a few things I can do to make this picture more special, set some more minors to 0. For example, obviously I could make 3 parallel to 1 and 2. Right? So that's one kind of boundary. So that I have 4 there, and then 3 and 1 and 2. I could make just 3 parallel to 4. That's another kind of boundary. I could do something else which is a little more, looks a little more violent, but is, I mean, there's nothing wrong with it. I had 3 and 4 and 1 and 2. I could say, you see here it says that 2 is proportional to 1. I could just make the constant of proportionality 0. Right? I could just make 2 vanish. Or I could make 1 vanish. Okay? So if I do that, then I'd just be left with a picture, let's say, with just 1, or just with 2. That's still no problem. In fact, maybe I'll just mention this point now. All we need, in order for this to be an honest k-plane in n dimensions, all we need is that there is k vectors that span the whole space. That's all, right? Because we just want a single non-vanishing minor. If we don't have that, then that means it's not really a k-plane. It's a k-1 plane. It's a lower plane, right? So we want it to be a full dimensional k-plane. But that doesn't tell me I can have columns vanish, no problem, right? I just need k of the vectors. I need at least 1 minor to be non-vanishing. That's all. Right? OK? So what do these kind of boundaries look like in this picture? Well, so some of them, well, they all are reasonable. Like here, all we see here is those 4 ordered points, right? So that's where the ordering is reflected in the picture. So here 3 can slide to be on top of 4. That's one kind of boundary from here. I could have 3 slide to be on top of 1, 2, 3. Or I could, now that 1 and 2 are on top of each other, what does sending 2 to 0 mean in this picture? If I send like 2 to 0, that just means when I extend out the picture of the ray to draw 1, 1 is just gone. I just don't see 1 anymore. I don't see 2 anymore, right? So here's another boundary. Just 3, 4, and 2 is gone. I deleted 2. OK? Sorry, 3 and 4 are still separate in this picture. Sorry. Thank you. OK, and so you can keep going. So where can we go from here? We can just draw it in this picture. So from all of these pictures, all I'm going to get, for example, from this one, I might get 3, 4, and just 1. OK? So I can delete any one of them. What I can't do is bring all the points on top of each other, right? I can't bring all the points on top of each other. That's the thing dropping. So all the minors would be 0 in that case. Because I need to have 2 independent points, 2 vectors. Okay? So I can't bring all the points on top of each other. But I can do everything else. So, and you see from all of them, all I'm going to get is something like this. 2 consecutive guys on top of each other and another guy. So also from this picture, I can slide to bring 3, 4 on top of each other. I can bring 3, 1 on top of each other. OK, that's kind of cool. 3 and 1 didn't look like they were consecutive. But I can do it now because 2 is gone between them. OK, so I can get things like this. I can also get 4 and 3 and 1 on top of each other, and so on. And finally, what can I get at the bottom? I can just get every pair. Every pair ij can occur as something at the bottom. OK? All right. So you see that the boundary structure of this space is a lot more interesting than it was for the simplex. So if you count all of them, you can find there are 4 of these boundaries, there's 10 of these boundaries, there's 12 of these boundaries, and there's 6 of these guys. Okay, so you can just go, we've drawn representatives of all of them.
So when you delete it, 2, you're counting it as a separate boundary?
Sorry?
If you delete or not delete, like in the 1, 2, 3, if you
Yes.
2 or not, you're counting that as a separate boundary?
Yeah, so one boundary here is deleting 2, okay? Another boundary is deleting 1. But you see, there are many ways of getting to this boundary 3, 4, 1. One way is from here. I can delete 1, I can delete 2 and get to the boundary 3, 4, 1. Another way is here. I could bring 3 and 4 on top of each other, and I end up on 3, 4, 1. Okay? So we'll defer talking about this later. I could draw you a sort of nice picture of a square pyramid here to kind of tell you how all these how these different boundaries are related to each other. Okay? So if you actually look at these number counts, 4 minus 10 plus 12 minus 6 is equal to 0. Okay? And so that's kind of like an Euler characteristic. If you thought of it as well, if we go backwards, vertices minus edges plus faces minus top faces is equal to 0. So that might make you think that these things can fit. We're using this language of boundaries, right? Maybe there really are boundaries. So there's some space, and I have some codimension 1 boundaries, and codimension 2, codimension 3, codimension 4. The fact that this Euler sum works is encouraging the idea. It kind of looks like a ball, right? There are some, so that's, but yeah, so that all that intuition is correct, but it's a curvy space. Okay? It's a curvy space, and we cannot actually realize literally this boundary structure for the full 4-dimensional object as a polytope. So we'll come back to these points later, but. Okay, so that's G24. Let's see slightly more vividly. So what does this look like for G2n? Just at the level of picture is exactly the same thing. G plus 2n. I just have, it always looks like some configuration of vectors, but they end up being ordered in this interesting way. Or I can draw one of these pictures, 1, 2, 3, up to n. Okay? And but let's now look at a slightly at the one higher dimensional example, just to get some more intuition for what's going on. So I want to look at what G3n looks like. Okay? And now for G3n, I'm going to have, again, some configuration of now 3-dimensional vectors in some interesting, very bad at drawing 3-dimensional vectors, okay? But again, they'll all be pointing in some direction, okay? So they'll all be on the same side of some hyperplane. That's very, very easy to see. And so because of that, and for the same reason, if I want to visualize it, I can imagine slicing it with a plane and getting a polygon, okay? Or some shape, right? So let's draw that picture. So they're really honest 3-dimensional pictures, but just like before, just to visualize, we could go down 1 in dimension. I want to do the same thing here, because it's going to allow us to make contact with some things that we've seen already before. Okay, so what does it look like? So now, after I go to this effective 2-dimensional picture, I have a bunch of 2 vectors. And now, what does it mean for all the minors to be positive? Okay, asking for all the minors to be positive, all the A, B, C for A1 less than A2 less than A3 is exactly asking for this polygon to be convex. Okay, so we have a convex polygon. So that's what we saw before, right? That just says that every triangle in this picture is oriented the same way. So I have to get a convex polygon. So you want to visualize G2n, drop down to one dimension as a bunch of points on a line. But they're ordered. That's a surprise, is that you just thought you were talking about all minors, but it turns out that they actually have to be ordered. Okay, so as a consequence of these nonlinear relations, but it's sort of obvious from the picture, they have to be ordered. Similarly here, I just said all the minors are positive. All the minors are positive, but somehow that forces the picture to look convex. And again, we can see the richness of the boundary structure. We see it even more vividly in this example. So here, let's say I wanted to go to the boundary. Naively, I have all these minors. They're all positive. Let me take one of them. I don't know, 1, 3, 5. I want to take the minor 1, 3, 5 and send it to 0. Can I do it? Sure I can. I take 1, and I send it screaming towards a line 1, 5. Okay, I want it to land on the line 1, 5, because then 1, 3, 5 would be positive. But oops, before I get there, I hit this configuration where 2, 3, 4 is 0. Okay, so I can't set 1, 3, 5 to 0 without sending something else to 0, right? And that something else involves the consecutive columns. Okay, so this is what all the codimension 1 boundaries look like. All the codimension 1 boundaries of positive G3n, for this reason, all the codimension 1 boundaries correspond to sending I plus 1, I plus 2 to 0. Okay? That wasn't built into the definition of the space, right? But somehow it comes out. Demanding everyone's positive actually forces that the consecutive minors matter. Okay? And those are the codimension 1 boundaries. Yeah. No, we haven't deleted anything. Yeah, yeah. No. 3 is still alive and well. Okay. So if you want to go back to the full 3-dimensional picture, just imagine drawing a cone underneath all of this. Take this thing, add a pointer to the origin, draw anything in those directions, and that's it. Right. And choose any vector in any point on those rays. That'll give you some configuration in G3n. As I said, this is purely a visual device to allow us to drop 1 in dimension, and it's useful for G2n and G3n. Okay, so okay, but let's keep going here, just to get an idea of just how rich the boundaries are, right? So all we're asking is how we can take this convex polygon and degenerate it more. Okay, so what's the next thing I can do? I don't know. I could put 4 on the line 3, 5. That's one thing I could do. I could take 3, which is already on the line 2, 3, 4, and slide it so that it's on top of 4. I could take 3 and slide it on top of 2. Okay, let's say I've done that. So this is now another boundary now. I have 2 on top of 3. So this is a 1 lower dimensional boundary. Now I could delete 2, or now I could delete 3. Okay, so once the points are on top of each other, I can delete one or the other. Okay, and keep going. Okay? But you see how rich it is, right? The ordinary notion of boundary is greatly enriched in this story, right? We're allowing ourselves to move these points around. They can, I can slide them around. I can delete them. So it's a more interesting and much richer boundary structure. We are going to talk about the combinatorics of the boundary structure of the positive Grassmannian at great length in a few weeks, or maybe even in 2 weeks. But for today, all I want to do is define the object and give you some idea of what its properties are. You know, what we've seen already is that it's a generalization of a simplex into the Grassmannian. It needs an ordering, and something about the consecutive minors is an emergent feature of this definition, that the consecutive minors matter, and the codimension 1 boundaries are just when the consecutive minors go to 0. And then there's a much richer kind of boundary structure as you go further down.
Just some perspective.
Yeah.
Is the point of this to like tessellate this object?
No, we're not. At the moment, we're not. So let me say a little bit about. So first, it's mathematically an obvious natural generalization of the simplex. Okay. What we're going to find is that it's going to pay off to understand the boundary structure of this thing. Okay. because, and this is not obvious at the moment, but from this definition, just k-by-n matrices with positive minors, and it will turn out that every one of the boundaries of this space, both the entire space itself and every one of the boundaries of this space, in other words, trying to understand the answer to the question, how do you describe all the k-by-n matrices where the minors are all positive to begin with? Okay, so that's a nice question. We're going to come to it in baby versions of it in a moment. But that's a sort of big question. Great. This is a space. It looks kind of complicated and nonlinear. How would I actually put coordinates on this space? I want to find some way to make sure I'm in this space. So I want to find some nice set of coordinates. I want to find a way of building a big 13 by 27 matrix, all of whose minors are positive. And the idiot thing to do is to just plonk down some matrix and write down a gazillion identities and try to solve them one at a time, right? But there's a more interesting way of doing it, which turns out to be to build these matrices gradually. And so you build bigger positive matrices by gluing together smaller ones. Okay? In fact, you start with the most basic positive matrices of all. I'm just giving you a clue of where we're going. So just five minutes of entertainment 5 minutes, which will become responsible 5 minutes in 2 weeks. Okay, but we start with the simplest matrices, a 1 by 3 and a 2 by 3 matrix. Okay, so just something that looks like that and something that looks like that, where we say that all these things are positive, right? X, Y are positive. This is in positive G13 and positive G23. Okay? With this matrix, you associate a picture. This matrix, you associate another picture, a black vertex and a white vertex. By the way, this is not, this is literally what our mathematicians friends did, not having any idea that the black vertices and white vertices meant something exciting for us, right, as physicists. Now you're just trying to build these more complicated matrices. So it turns out you just have to glue these pictures together. So you want to make a matrix in G24. You make something with 4 external lines, just gluing these black and white vertices together. And there's a rule for how to you associate these coordinates with each one of the black and white vertices. There's a simple rule that we will talk about for how to build a 2 by 4 matrix whose all minors are guaranteed to be positive. Okay? So the whole point is to build these positive matrices gradually from simple building blocks by gluing. And you want to build a higher matrix, you keep going. That's some 2 by 5 matrix. Maybe a 3 by 5 matrix anyway. Okay, and so on. Okay? So that's purely mathematically trying to understand, and it turns out if you want to understand all the boundaries of these pictures, then you take these kind of pictures and you delete some of the edges. Okay, so there are other smaller pictures with like fewer faces inside that correspond to all the boundaries. So everything about the boundary structure of the positive Grassmannian is associated with these pictures of black and white vertices, planar pictures of black and white vertices built out of elementary 3-point building blocks. Okay, so that's on the side of positivity. When we come back to talking about physics full time in about a week, actually maybe starting on Tuesday, we'll forget about all of this and we'll say, let's go all the way back to what we learned were the most fundamental objects for scattering amplitudes. There are the 3 particle amplitudes. And remember, there were 2 kinds, the plus plus minus and the minus minus plus. And as super amplitudes, there were 2 kinds. And also, even more fundamentally, the 3 particle kinematics had 2 ways of being, with the lambdas parallel, the lambda tildes parallel, right? So the 2-ness, the black and white, is there, right? Is there as a feature of 3 particle amplitudes. Then we can sort of decide to play. Forget about Feynman diagrams. What would we get if we just glued these objects together? Okay? Everything would be on shell, but we take these on shell amplitudes and we glue them together to make more and more complicated pictures that there are not Feynman diagrams, there's no virtual particles. We'd call those things on shell diagrams. Right? Those on shell diagrams look exactly like these pictures. But as it turns out, if you want to compute the functions that are associated with those on shell diagrams, then if you do it in the absolutely dumbest way, by integrating over the on-shell phase space in the middle, everywhere, it gets sort of more and more complicated. And you realize that it's more and more complicated because you did not quite understand the 3 particle amplitude properly. Okay, so you go all the way back to the 3-particle amplitude and represent the 3-particle amplitude in the conceptually better way. Doing that forces you to introduce these little variables, these little G13s and G23s, which you don't even realize yet are G13s and G23s. But once you do it like that, the physical way of gluing these things together literally builds the same positive matrix. Okay, so there's a one-to-one correspondence between on-shell processes and facets of the positive Grassmannian. That's the connection. Okay, it's not obvious but that's the connection. Now the reason it matters is that you later learn that all the amplitudes can actually be built out of these on-shell processes. For example, a BCFW recursion is just a simple example, a kind of a fundamental example of this way of gluing together 3-particle amplitudes to make more complicated things out of simpler ones. This is why I've deferred doing explicit computations, because once we understand this connection, all the computations are done at the level of pictures. Okay, so we don't have to explicitly keep track of things as we go along. But okay, that's the end of the aside. That's why these things matter. There's this interesting mathematical object. There's an interesting physical thing that you might want to care about. What happens when you just glue on-shell processes together? The remarkable thing is that they're tied to each other, that they're basically the same thing. Okay, yeah. And as I've said many times, that's just halfway there, right? Already that's a remarkable connection. That on all of this amazing combinatorics that we're going to see is reflected in the answer, is reflected in these on-shell processes. So, but it's halfway there because then we're going to have to understand why things are glued together in a particular way to give us the final amplitude. So that's the, but this is the first step. Yeah.
These Grassmannians are supposed to come to the inside of something which is set by the kinematical data.
Well, yeah. So here we're not seeing any kinematical data yet. Okay. So here we're just talking about the abstractly the inside of the space. And indeed, when I say that we have these on-shell processes, that seems to depend on lambdas and lambda tildes. There's no lambdas and lambda tildes anywhere here. We'll see how they're related. And it has to do with what I said a second ago, but it's not going to make sense now. It really goes back to the 3-particle amplitude. The way we write the 3-particle amplitude was too lazy. Okay, it was too clever. Okay, whenever you're being too clever, you're doing something wrong. Okay, it's slightly too ingenious. You have to do it in a slightly dumber way, in a slightly more manifest way. But that slightly manifest way forces you to introduce some variables in the problem that you don't see when you just write down the answer. So in doing that, the computation of an on-shell process involves the integration of a lot of auxiliary parameters. Those auxiliary parameters are going to be this Grassmannian. Okay? Now, when I ended last time with the definition of the full amplitude to all loop order in the kinematic space, you don't see any of this. Okay? So we have that's why I say we're back in the valley. We have 2 more mountains to climb before we get there. Okay? So, but it's all important, and they all have a role to play in this story. Okay. All right. So let's go back. And I want to say a second remarkable thing. Oh, so first we just drew pictures, but for G24. Actually G2n in general, but it's very easy to sort of use nice coordinates to describe what things are going on anyway. So let's just say everything in coordinates. Okay. So what's, again, the absolute dumbest thing you would do? The dumbest thing, certainly the dumbest thing I would do, is gauge fix something that looks like this. Okay, so in that gauge fixing, what is the positive Grassmannian? Well, 1, 2 should be positive. That's good. I made it positive. Then I just have a lot of formulas. I have 1, 2 is 1. That's positive. 1, 3 is y3 is positive. 1, 4 is y4. That's positive. 2, 3 is negative x3. So that should be positive. So maybe I should have put a minus sign there then. Okay, so if I do that, then x3 should be positive. 2, 4 is negative x3 y4. Negative y3 x4. Well, let's, yeah. 2, 4 is just negative x4, sorry. So let me put a minus sign there. I was jumping. OK, and 3, 4 is minus x3, y4 plus y3, x4. And finally, 1, 4. So we did, no, we have everything now. OK, so all these things have to be positive. OK. So, there's a slightly annoying 2 by 2 matrix there. You can do another gauge fixing, which is more brainless. So here's another gauge fixing. Right? Now it is easier, because now 1, 2 is just B2 is positive. 1, 3 is just 1. 1, 4 is B4 positive. 2, 3 equals A2 is positive. So all these variables have to be positive. And now here's the interesting thing. Well, we can see it in any gauge fixing, but it's easier to see it in this one. All right, so here are our conditions. And once again, we can see some of the things that we saw in the picture before. All I need to do is, everyone has to be positive, it's true. But notice that by the time I make sure that 1, 2, 1, 4, sorry, 1, 2, 2, 3, 3, 4, and 1, 4 are positive, right? See, that already forced B2, B4, A2, and A4 to all be positive. Then 2, 4 is automatically positive. Very nice. I don't have to impose it anymore. Notice, though, I have tacitly made 1, 3 positive. OK? OK, so here I would discover the same things. I just have to work slightly harder, right? So by the time I say 1, 2, 1, by the time I say exactly the same things, anyway, we'll again see that having put 1, 3 positive, the positivity of the x4 will be redundant. Okay? So it's sort of obvious here, right? By the time you say everything else is positive, but 3, 4 is already saying that x4 is bigger than something, x3, y4. So it's certainly positive. Okay, so again, 2, 4 is redundant, having made 1, 3 positive. OK. But this is obviously the slightly nicer gauge fixing for G24. Because all we need is that those variables are positive and they run from 0 to infinity. OK. So in other words, so we can think of at least in one coordinate chart, it covers almost all the Grassmannian, but is missing the regions where the minor 1, 3 is 0, right? So this gauge fixing doesn't cover everything, because it forces the minor 1, 3 to be 1. So there are regions where the minor 1, 3 is 0. But fine, this is covering almost everything except that lower codimension locus. OK, so here I just have to have that all these variables are positive. And now there's, so that's the analog of the simplex in G24. Now we can keep going and ask for the other things that we've seen that we could do with simplices. For instance, there's a canonical form associated with a simplex. Okay? So what is the canonical form that should be associated with the positive Grassmannian? I want to find a canonical form with logarithmic singularities on all the boundaries of G24. And again, I'm going to be a little bit loose today, but just so we see what the answer looks like. What should this form be? Okay, let's first do it just most dumbly from what we see here, and then just write down the answer and see that they're and just write down the only answer that we could have had, but, and just see that they match. So what should the form be? And these coordinates, all these variables, they're independent. They all go from 0 to infinity. So what could the form be? It's just the d log of all of them, right? So if this form exists, omega for k equals for G24 would be d log A2, d log A4, d log B2, d log B4. OK, well, so this is And now let's write this more invariantly. So remember, the D of all these guys was just that top form, universal top form on the Grassmannian. Okay? So this thing is just D 2 times 4C mod GL2 is the top. Right? Now what is the bottom? A2, A4, B2, B4 were just all these minors. So it's over 1, 2, 2, 3, 3, 4, 1, 4. And that's it. Okay?
How do you know there's no 1, 3?
Very good. There could have been a 1, 3, but this, you see, we're already done. Okay? So there's no, first, just by weights, we're already done. Okay? Note that this thing upstairs has because of the 2, every column appears twice. So all the weights cancel upstairs and downstairs. We need to have a total of 4 minors downstairs to make up for the GL1 weight of this thing upstairs. Okay, so that's all it could have been. What's another reason why we couldn't have had a 1, 3 downstairs? That's right. There's no pole. We can't encounter a pole when 1, 3 goes to 0. There's no codimension 1 pole where 1, 3 goes to 0. Okay? Now, of course, this looks really familiar, right? We've seen this in the Park-Taylor formula. Okay? But we were not talking about forms before. Okay? If we were talking about a form on lambda space, then the form on lambda space, which would be D2 times n lambda mod the GL2 that acts on the lambdas, multiplied by the Park-Taylor factor, would have been this, this canonical form on the positive Grassmannian. Right? So in fact, let's keep going and look at the, and just say what the answer has to be in general. Right? So for G2n, let's say for positive G2n, if there is a canonical form, there's only one thing it could be. Right? Because we know it has to have n minors downstairs in order for the weights to work out. We know it's going to have poles on all the consecutive guys going to 0 and nowhere else. So that's it. That's all it could be. 1, 2, 2, 3, and 1. So if there is any such thing as the canonical form associated with the positive Grassmannian, this has to be the answer. Okay? So let's see how this works for G25, actually. Doesn't matter here, because the whole form, the whole form only is defined up to an overall sign. Remember, the whole form only has it has an orientation. Okay, so here I prefer to write it in a way that makes the cyclicity more manifest. Okay, so let's already see how this works for n equals 5, where it is interesting. So this is a 6-dimensional space. It's 2 times 5 minus 2 equals 6-dimensional. Okay? And so let's choose some coordinates. I want to make it look as much as the nice coordinates for G24. So I'll start with what I had in G24, and then, OK, then life gets complicated at the end. So let me put a minus x5, y5 up here. OK? It's my 2x5 matrix. OK, so let's look at what the positivity conditions are. Now there are 10 minors. So this is going to be slightly more interesting. So 1, 2 is y2. 1, 3. So let's first look at the consecutive guys. 2, 3 is x2. 4 4, 5 is interesting. Oops, is negative y5 x4 plus x4 x5 y4. 1, 5 is y5. Okay, those are all the consecutive ones, and then I have like 1, 4 is w is y4, and I did 1, 5, so let me do 2, 4 is x2 y4 plus y2 x4. And 2, 5 is x2 y5 plus y2 x5. This 3, 5 is x5. Okay. Who am I missing? 2, 3, 4, 4, 2, 5, 3, 5. Oh, 1, 3, I'm sorry. 1, 3 is just 1. Okay. All right, good. Okay, so now you see it looks slightly more complicated. Okay, so, well, let's already notice something interesting. So all of these guys are all these things. A lot of them are manifestly positive already. So we have 1, 2, 3, 4. Yeah, so all these guys are yeah, they're all positive already. But in fact, so all these variables are positive. But x5 has got to be more than just positive. See, from here, I see that I have to have x5 is bigger than y5 x4 over y4. It's a good thing that I know y4 is positive, so I can divide by it, right? So to get this inequality, okay? So x5 is not just positive, but it's bigger than that. So notice again something interesting. Let me now draw this picture. Now, this picture is just denoting minors. It's just a way to remember minors. Okay, so this is meant to, that line is meant to denote 1, 2, 2, 3, 3, 4, 4, 5, and 1, 5. So we have to have that all these guys are positive. Okay, and we've also said that 1, 3 is positive. That's part of our gauge fixing. But now, so notice the sort of cool thing. The second we say 1, 4 is also positive, everything else is forced to be positive. Right? So we said y4 is positive, 4, 5 is positive, then everything else is forced to be positive. Right? So 2, 5 is positive, everything else is positive. Right? So this generalizes the phenomenon we saw before. So what is the analog of this phenomenon that we just saw in G24? We would draw a square instead. So here we have 1, 2, 2, 3, 3, 4, and 1, 4. But we said that if I say 1, 3 is also positive, then 2, 4 is automatically positive. Or I could say that 2, 4 is positive, and 1, 3 is automatically positive. Right? So that shows you the kind of interesting interrelation between the relations between the minors and positivity. Okay? You don't have to say they're all positive. It suffices to say that some subset of them are positive, and that guarantees that all the rest of them are positive. Okay? So that's another phenomenon that we're going to see repeatedly, and we're going to try to understand. And it's going to play an interesting role in the story. Let's go back to this picture. I could have also said something else. I could have said, just say that 3, 5 is positive. Okay? Let's say I said 3, 5 was positive. Then that would have been enough from this equation to force the one that we didn't know, to force, oh, sorry, this one we're imposing already. I apologize. Yeah. If I say 3, 5 is positive, then sorry, I just want to see what the consecutive guys are already forcing. So yeah, good. Sorry, excellent. So we're enforcing all these. Once I know that x5 is positive, then that tells me that y4 is positive, okay? And that tells me 1, 4 is positive. Okay, so I could have also given you this guy, and then just saying these are positive forces everything else to be positive as well. Okay, so you kind of see a pattern here in these pictures, right? I have to tell you that all the minors on the outside are positive, and then just some more. But what are the some more that I need? Well, I kind of just triangulate the inside of this picture, right? I can take this one or that one. Here I can take this one, I can take that one, and those suffice to say that all the minors are positive. Okay, so that's that phenomenon. But now let's return to the canonical form. Okay? Now let's return to the canonical form. So this is what our space is then. Our space is that we have to have x2, y2, x4, y4 positive, but x5 not just positive, but bigger than that amount. Okay, so what is the canonical form? Again, so naively, the canonical form here would be dx2 over x2, dy2 over y2, dx4 over x4, dy4 over y4, and then dy5 over y5. But the last one is dx5. And x5 doesn't just have to be bigger than 0. It has to be bigger than this thing. So it has to be x5 minus y5 x4 over y4. And of course, that y4 here just combines with that to give me a minor of the matrix. Okay? So this ends up just being, once again, d2 times. But this now makes it clear that there is a canonical form, right? I mean, I've found a way to parameterize the space with just simple independent positive coordinates. So this is what the canonical form is. So the form is d2 5c mod gl2 over all 5 of the minors. Okay, which is all it could have been. It's all it could have been from the other reasons that we said. Right? If the form existed at all, these are the only poles that it could have, and then you're done. Okay? Here we just verified it explicitly. But there is an interesting point. There are many new things that start happening in these curvier spaces. And here's one of them. You see, already in this example, you might have thought, I'm telling you this is a form with logarithmic singularities, right? It's a 6 form. It's a 6-dimensional space. It's a top form on a 6-dimensional space. It's a 6 form with logarithmic singularities. That means you have to be able to take 6 residues, right, to get all the way down to a point at the bottom. Well, very naively, you can't. How can you take 6 residues? There's only 5 poles. Right? When we have these simple simplices or even polytopes, we didn't encounter this problem because every single pole was just a linear factor. And setting it to 0 was, OK, it's very obvious what it meant. It knocks you down 1 in dimension. Right? And you have to have as many poles as there are the dimension of the space plus 1 in order to be able to get there. Right? But what's going on in this example? Well, we can see, since we just wrote down the answer, the form in this case, when I write the whole thing, is dx2, blah, 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 up to dx5 at the end, over x4, x2, y2, y5. And then we have this last factor from the last minor, y4, x5 minus y5, x4. This came from the, in these coordinates, it came from the 4, 5 minor. OK? And so what's going on? We only have 5 poles. Weren't I screwed? Right? The reason is let's say I take a residue on like x4 goes to 0, right? I'm just taking residues as I go. I'll take a pole at x4 goes to 0. That term drops out, and this minor factorizes. So then in the next step, I can actually set it to 0 in two different ways, by putting either this to 0 or that to 0. Okay? So that is a phenomenon that's ubiquitous in the kind of residue calculus that we're going to be dealing with. So these are not ordinary residues in the completely standard sense that you define a residue by giving a bunch of polynomials that of the right number that vanish in the right place and so on. They're not like that. They're very small modifications of that, but this is a totally ubiquitous phenomenon. And we saw it already here in G25. Of course, as you go to high KNN, the difference between the number of poles downstairs and the amount of and the dimensionality of this straight becomes huge, right? There's n poles downstairs. The space is k times n minus k dimensional. Okay? So the vast majority of this structure of the boundaries is then happening in how these poles factorize into smaller pieces as you start setting things to 0 and going down, right? And that's exactly what we see sort of reflected in the geometric pictures, that you start with just this big floppy convex polygon, and then you have to make some sides. But now you can do lots of things. You can go there, you can go there, you can now start collapsing other sides in more interesting ways. All of those many different things that you can do at that step is reflected in different ways that these polynomials downstairs start factorizing as you go onto these more special configurations. Okay, so we see it already in this very simple example.
Does this mean that the facets of the positive Grassmannian don't meet each other?
They meet. They absolutely meet. Yeah, they even meet transversely. No, everything is. But I'll say something about that. We'll talk about this at some length in 2 weeks. Okay. So I just want to do one more different thing in this lecture, and then we will we'll come back to those things later. All right. Okay. By the way, if I go back to G24, just a minor point, but just have some fun. So in these coordinates, again, the form is that. And we can see a lot of the boundaries of the positive Grassmannian by taking residues in the obvious places here. So if I take x to 0, that residue, when x is 0, what is it doing? It's making 2 and 3. So if I send x to 0, it's making 2 and 3 parallel to each other. Okay. All right. If I then send, after having sent x to 0, if I send y to 0, it's deleting 2. Okay, so sending y to 0 is deleting 2. If I then send z to 0, it is making 4 parallel to 1. And finally, if I send, I don't know, w to 0, it's deleting 4. So there's a sequence of ways of sending x, y, z, w to 0 in many different ways, and we see a bunch of the boundaries of the positive Grassmannian. There are the other boundaries at infinity. In these coordinates, those boundaries would be at infinity, right? And well, all you have to do, if you want to see it explicitly in this way, is you just let's say you want to see one of the boundaries where 1, 3 is going to 0. This is a very stupid gauge to do that in because you've set 1, 3 to be 1. So you just fix a different gauge. In that other gauge, you'd have another set of D-log forms, and you'll see a bunch of the boundaries there. Okay? And of course, many of the boundaries will be in common in these different gauge fixings. But that's the sort of magical thing about this simple form, is that it puts logarithmic singularities on and only on the boundaries of this curvy generalization of a simplex. Okay, so that's it. That's the entire definition of the positive Grassmannian. And we just saw the canonical forms for G2n. So let me just end by telling you what the canonical form has to be for general GKN. So for general GKN, again, so this is summarizing everything we said in this lecture. The positive Grassmannian GKN is the space of k by n matrices C alpha A, where all of these minors are positive when they're ordered. And there is a canonical form associated with this space for k and n, which, what can it be? So there's some dkn C mod GLK. But by exactly the same logic, we saw, at least visually we saw in the G3n case, that again, the codimension 1 boundaries involved consecutive minors. 1, 2, 3, 2, 3, 4, 3, 4, 5 goes to 0. Okay, so having seen it for G2 and G3, you can trust me that that pattern is true, that the codimension 1 boundaries are just when the consecutive minors go to 0. Okay? And therefore, we have to have those consecutive minors downstairs. And nothing else downstairs, because these are the only codimension 1 poles we're going to encounter. Okay? So you just plonk all the consecutive minors downstairs, and you're done. That's all it can be. Now here, too, we have this interesting interplay that we've seen many times already, but now we're seeing it in a fancier context of these curvy geometries. That this is some complex form. It doesn't care about positivity, doesn't care about anything. Right? It's just some complex form. It has some singularities. It has some strata of residues that you can start taking. Right? So in fact, if you never knew about the positive Grassmannian, about even the word positivity, you might run into this form, and you might start enjoying looking at what the boundaries look like, and you'd find that the boundaries have a very interesting kind of structure. That the boundaries look like 2 columns, 3 consecutive columns become, that minor goes to 0. So those columns become coplanar, and then this happens, and that happens, and so on. And after a while, you might see that all of those conditions are associated with some positive real space. Okay, so exactly some positive real space that's associated by these by saying that all these minors are positive. Okay, that all the strata that you get as the real geometric boundaries of the positive space are reflected in the residues of this form. Okay? And then of course we see that this form and the geometric space are sort of tied to each other. They tell the same story. Okay? Now this is of course the way we ran into these structures as physicists, is that one way or another we ran into the forms first. And you start looking at the singularities of the forms, and you see a very intricate pattern in the singularities of the forms. And then you're awakened to the idea that that pattern and the singularities of form are trying to tell you a geometric story. And you look for some geometry to associate with these forms. OK. So that's it for the. So that's just the flat-out definition of the positive Grassmannian. This is the claim for what the canonical form is. Next time, we will come back to the world of lambdas and lambda tildes. Okay, so next time we'll come back and think about physics again, and we're going to begin by thinking about momentum conservation. Okay, we're going to think about momentum conservation in a new way. It might surprise you a little that we're going to learn anything interesting about the world by thinking about momentum conservation, but in fact, this is sort of part and parcel of the philosophy of things that are happening in this course. Momentum conservation is something obvious in ordinary local quantum field theory because we have the interior of space-time. It's obvious because we're integrating something over the interior of space-time, and we have translational invariance in that interior of space-time, and that's why it's so obvious we even strip it off from everything that we talk about. We don't care about it. But from this point of view of the person who lives at infinity, who doesn't know about the interior of space-time, momentum conservation is strange. They don't know that there's an inside of this space-time. Somehow, these amplitudes that they get have this magical, weird property that they are 0 unless all these on-shell things add up to 0. Where the hell is this coming from? They don't know why. They don't know there's an interior of the space-time. So understanding the origin of momentum conservation is interesting. Okay? And this is something that everyone who's tried to build a hologram in flat space runs into this issue. Andy and his friends who think about celestial amplitude, you know how exciting momentum conservation is. It's weird for momentum conservation to be something exciting. But anyway, it's not weird from this holographic point of view, and that's what we're going to begin with next time. We're going to think about momentum conservation from a point of view that will make it natural to introduce Grassmannians, and we'll take it from there. OK, thanks a lot.